Hello, Chem 1B. This is chapter 22, lecture video 2, and we're going to be introing coordinate complexes. And before we can really talk about coordinate complexes, we got to talk about a new type of bonding known as a coordinate covalent bond. Now, we know what a covalent bond is because we learned about it in Chem 1A. And a covalent bond, if you don't remember though, is when electrons are shared equally between two atoms. Hydrogen is a great example, right? So if I have a hydrogen Lewis dot structure, or a Lewis dot symbol, I know that hydrogen has one electron, one valence electron. Now it can come together and share these two valence electrons and form a covalent bond to hold it together. Now this is a non-polar covalent bond, hence shared equally, right? Polar covalent bonds, electrons are being shared, but they're not perfectly being shared equally. In a coordinate covalent bond, we have something a little bit different going on. It is the sharing of a lone pair of electrons between two substances, but really only one substance is donating the lone pair. For instance, right, if we have NH3 here, NH3 has a lone pair on the nitrogen, and hydrogen plus has no electrons at all. So what can happen here is we can form NH4 plus ammonium by having the nitrogen share one of its lone pairs, or its only lone pair, with the H+. In other words, we basically have something like this going on, right? So we have this lone pair on the nitrogen, and we have this H+ here. This lone pair forms a coordinate covalent bond with the H+, giving us an H4+, right? So one of these four bonds here is actually a coordinate covalent bond, and the other three are just simply covalent bonds. Now, this is how most of our complexes are formed with transition metals. It doesn't have to be a transition metal, as I showed with the nitrogen here, but most of the time this occurs with transition metals. And this is because transition metals can accept lone pairs into their vacant d orbitals, forming coordinate covalent bonds. Now, going back to something we learned about at the very beginning of chapter 16, or sorry, at the very end of chapter 16, is a Lewis acid, if you remember, is defined as something that accepts an electron pair. The metals in a coordinate complex are Lewis acids, as they accept a lone pair of electrons from the ligand, or the Lewis base in this scenario. The things that attach to a metal center we usually call by a special name ligands. And the ligand is generally the thing that's going to be donating the lone pair of electrons, and it attaches to the metal center. So let's talk a little bit more about complex ions. Complex ions are ions containing multiple of atoms. Usually a metal atom is involved in a complex ion. Something like this is a complex ion. We saw them first in chapter 16, or in actually our Le Chatelier's principal lab. But in this case, this is what we call a coordination compound. Complex ions are coordination compounds. In this case, we have Ni in the center here. Each one of these bonds here, all 6 of them around the nickel, are coordinate covalent bonds, right? All of them are due to water, H2O, right, if we draw its Lewis structure, sharing one of its lone pairs to the Ni2+. These compounds or complexes are very common, and so we need to talk a little bit more about them. As you can kind of see here, hopefully you remember from Chem 1A and Vesper, V-S-E-P-R, that this is an octahedral. Not with a T and L. Again, the H2Os in this case in complexes are called ligands, L-I-G-A-N-D-S. If if you're like British, a lot of times my British instructors would call them ligands, but everywhere in the US I've heard it as a ligand, so pronounce it how you will, I don't really care. The overall charge on this coordination compound is determined through the metal ion and the ligand, but since water is neutral, it's really, in this case, just the metal ion, right? We have 6 waters, all the waters are neutral in this compound here, so our charge is coming straight from the metal in this case. But if we have a ligand that's charged, that will also affect the charge on the complex ion. So nickel has a 2+, water has 0. We have 6 waters, 6 times 0 is 0. Our overall charge is going to be 2+. This is going to be important for other compounds that don't have neutral ligands, right? Because then you're going to have to combine the two. Can't find nickel with 6 waters attached to it on a shelf. Why? Well, the reason is because you can't find any positive or negatively charged thing on a shelf. They don't exist by themselves. They have to be dissolved in water if they're going to keep that charge. Or they need to be attached to what we call a counter ion. Counter ions balance charge. For instance, we could find this on a shelf, right? Nickel with 6 waters and Cl attached to it. This being Cl minus, there are 2 of them because of the 2+ charge on our complex ion. That is totally findable on a shelf because it has a counter ion. Counter ions will allow it to be in the solid state and isolated. It's important to notice that these Cl's are not part of the brackets. The brackets are my complex ion, and we use brackets to indicate complex ions. Everything outside of it would be part of what we call a counter ion. Chlorides are bound through ionic interactions, not through coordinate covalent bonds. So these waters here are attached to the nickel via a coordinate covalent bond. The Cl's are not. They're just straight up ionic interaction. We have a negative charge on our Cl's, we have a positive charge on our complex ion. They're attracted to each other. So it's a different type of bonding, and that's why it's important to keep them separate from each other. A ligand that only forms one bond with a metal center is called a monodentate ligand. However, like water actually can only form a single coordinate covalent bond with a metal. However, and there's a bunch of others like Cl, OH, NH3, CO, all these guys are monodentate ligands. They form a single bond to the metal ion. But there's things called bidentate ligands or tridentate or hexadentate, or typically after bi, we usually just call them polydentate ligands. These two both can form 2 bonds to the same metal. And if we look at like that nickel 2+ example, we have an O attached to carbon, and another O, and a double bonded O. This would be kind of, right, so this part here is our carbonate, and you can see how the 2 oxygens can both attach to the same center atom. That is what we mean by a bidentate ligand. Now, oxalate can do something very similar. A ligand that forms multiple bonds, more than 2, is called a polydentate ligand. These are very actually important in a lot of biological systems, and we'll talk a little bit more about application of this in a second. So let's classify the method by which the following ligands are attached to the transition metals. So if we look at these, we can see that each one of these is attached via 1 bond. These are monodentate ligands. Let's look at something else. It's a little bit harder to see. These are bidentate ligands, and you can kind of see that we have this bond here attached to this guy, attached to that guy, attached to that guy, and then back attached to the metal. This whole thing is one substance, and this is a bidentate ligand. There are 3 bidentate ligands on this cobalt, right? We have another one here. They're all attached to each other in a line, and the same thing here right? So we have these 3 bidentate ligands on this one, on this cobalt 3 plus center. This one's a little bit crazier. This is a hexadentate. We're going to call it polydentate, but you can kind of see this guy attaches this oxygen, attaches this carbon, attaches this carbon, attaches this nitrogen. The nitrogen attaches again here, but then we attach this carbon, attach this carbon, attach this nitrogen. That attaches there. It goes up here, attaches there. It also goes over here, attaches there. This one also goes down here, which attaches there and then back up. This is one ligand. And it's attaching in 6 different places around this lead center. It's kind of neat. It's called a polydentate ligand, and they are extremely useful in isolating metals and other applications too, and we'll talk about that. So let's look at this guy. Ugh. These need to be fixed. It is a tridentate ligand. Classify the method by which the following ligand probably attaches to a transition metal, and we got this structure. How do we know that it's tridentate? Well, remember, ligands bond to metal ions by donating lone pairs. We have 1, 2, 3 lone pairs on this ligand, and they're separated by a good distance because they have a bunch of carbons in between them. If they were right next to each other, like for instance, if we had another lone pair here, these two couldn't probably bond to the same metal just due to like angle issues. They're too close together. The angle doesn't work. But since these guys are separated enough, this is going to be a tridentate ligand. All right, again, a polydentate ligand has another name as well. It's also called a chelating ligand. Again, there are other pronunciations of this word, but I've always heard it as chelating. Chelating ligands are really important for sequestering metals. Like if, for instance, we had some heavy metals that we wanted to get out of water before we could drink it, we could use chelating ligands to bond them and then pull them out of the aqueous phase so that we could then make that water safe to drink. An excellent chelating ligand is known as EDTA, or ethylene diamine tetraacetate. It's a mouthful. And you can kind of see here, it can bond in actually a bunch of locations. We have some lone pairs here. We have a lone pair here. Sorry, only 2 of them on that one. We have a lone pair here. We have a lone pair on this nitrogen. 2 lone pairs here, 3 there. This guy can actually, it's typically a hexadentate ligand, again, kind of like the one we saw previously. In fact, I think this is the ligand we saw previously attaching to lead. So it can attach to one ligand in 6, or one metal ion in 6 different places. Kind of neat thing. So here's it attaching to cobalt. These golden lines are this carbon chain here, and these carbons. Actually, so these are all shown by those golden ribbons. It's just a shortcut way of showing it because it's a complex structure, but you can kind of see how it all connects. Here is it actually precipitating out heavy metals from a water system, right? So you have all this like rustish color stuff. This is actually Pb2+ being isolated from an aqueous environment, because if you attach this guy to it, it tends to become less soluble and therefore separates out from the aqueous phase, which is kind of nice. So we're going to talk about kind of a really quick review of Vesper, but Vesper for coordination compounds is slightly different. Usually we only have 2 very common coordination numbers, and the coordination numbers are really how many things are attached to the metal center, or in how many places is there a coordinate covalent bond. So there are really only 3 major different types of coordination numbers we can have. So a coordination number of 2 means that our metal has 2 spots that it's forming a coordination covalent bond in. Typically, we're only going to, well, not typically, we're only going to see monodentate ligands with coordination 2s. So we have a ligand attached, we have 2 ligands attached to the metal center. It could be the same ligand, like this one, or it could be 2 different ligands. But the shape of this is only one possible answer. In coordination 2, we only have linear substances, or linear coordination compounds. In this case, we can also figure out what the oxidation number is on this Cu. You should just be able to do this. This isn't really related to structure, but we know this guy adds up to a -1 charge with 2 -1s here. So this had to be a +1 charge in this case. Not something to memorize, just something to be able to calculate. Here's another coordination compound that's a linear molecule. We have these 2 NH3s attached to the silver. What's its oxidation number on the silver? Well, it's +1. How do I know that? Well, because these 2 are both neutral. They have 0 charge. We have an overall +1 charge on the complex ion, so this guy has to be +1. Geometry is still going to be linear. Oxidation state +1. When we have coordination, when we have 2 things coordinated to our metal center, it's always going to be a linear geometry. Cool, so let's look at something else. Let's look at coordination, all coordination 2 compounds are linear. Coordination 4, there's actually both monodentate and bidentate possible. You can't have tri or hexa or polydentate ligands on this. It's either mono or bi. And there are actually 2 possible geometries. So you can have a tetrahedral structure like this guy, or you can have a square planar like that guy. And hopefully these names aren't new. They're definitely something that should be reviewed from Chem 1A. So if you don't remember what they kind of look like, these guys have a 109.5 degree bond angle. These are all 90 here between these guys. And across, it's going to be 180. Another 180, right? Remember that the ligands are the ones that are only inside the brackets. So in this case, we have NH3 as our ligands. 4 of them. Again, coordination 4 means we have 4 ligands attached to our metal center. Or 4 locations the metal is forming coordinate covalent bonds. The last one is coordination number 6. There's only actually one possible geometry, and it's, hopefully you remember from Chem 1A, going to be octahedral. You can have both polydentate or monodentate ligands present in octahedral geometry. So you could have bidentate, you could have hexadentate like we saw with EDTA. So there are a lot of applications of coordinate compounds, especially in biology. If we think about photosynthesis, the molecule involved in photosynthesis in plants is chlorophyll. Now, chlorophyll has this overall structure, and it's actually a coordination compound with magnesium. You can kind of see here we have this magnesium center, and the nitrogens in this guy are all bonding via coordinate covalent bonds with the magnesium. And so this is a chelating compound or a coordinate compound with a polydentate ligand, the chlorophyll being the polydentate ligand. And it helps transport magnesium throughout the plant, and it's very important to the biological processes. What about oxygen being carried in animals, right? So what's the molecule that carries oxygen throughout our bodies? Well, it's hemoglobin. And it has this big, fancy structure. But if you look at this group right here, and this group right here, and this group right here, and there's another one here, these 4 groupings inside these really weird looking pictures, this is just a giant graphical way to show the structure of hemoglobin. But those 4 groups there are what we call the heme group. And the heme group looks kind of like this. The heme group is a chelating ligand. It bonds to iron via coordinate covalent bonds, right, with the nitrogens again, because they have the lone pairs to donate. And the iron then bonds to oxygen, which allows us to carry oxygen throughout our bodies. It's pretty neat stuff. There is a lot of application of all of this going on in our bodies and in other systems as well, not just biological ones. Anyway, so as always, if you have any questions, please feel free to email me or come to a discussion session.